Okay, welcome back children. So coming to today's class, we'll be studying about electromagnetic waves. So it's a small chapter which is a culmination of all the concepts that we have studied previously from electrostatics, magnetism and matter, electromagnetic induction and so on. Okay, Maxwell has studied all the laws of electricity and magnetism, and finally using these laws he proved that light is an electromagnetic wave. And he could even prove that speed of light in vacuum is 3 into 10 to the power 8 meter per second by making use of these equations. And later on it was practically proved by Foucault that speed of light is 3 into 10 power 8 meter per second. Now coming to this particular chapter, we will be studying about displacement current, then Maxwell's equations, properties of electromagnetic waves and electromagnetic spectrum. So let us first begin with displacement current. So we know conduction current is produced by a battery connected to a wire. Okay, we know when you connect a battery to a resistor and a key, as soon as you close the key, current in the conducting wire, we call it as conduction current. But here we are talking about another type of current which is called as a displacement current. So to understand this displacement current, look at the diagram which is given here. It's a parallel plate capacitor with circular plates connected to a battery and a switch through an ammeter. Okay, we know that when we close the switch, as long as capacitor is charged, there will be a deflection in the ammeter, which says that there is a current in the circuit until the capacitor is completely charged. Once capacitor is completely charged, ammeter shows a zero deflection. But during the charging of capacitor, Maxwell took two different points. One point is just outside the plate, which is represented by Q. Okay, this is Q. And he took another point P, which is inside the plates of the capacitor. Okay, this point I am calling it as P. Now he found that when you place a magnetic needle near P, the magnetic needle showed a deflection. When you keep a magnetic needle at Q also, there is a deflection. To explain magnetic field at Q, we can explain by using Ampere's law. Say if you select a point at Q which is at certain distance, we can construct an Amperian loop. This loop is enclosing the conduction wire which is carrying a current, and we know magnetic field around a current carrying conductor is given by Ampere's law. Integral B dot dl is mu naught into I. But once you go inside this plates of the capacitor, if I apply the same Ampere's law at P, there is no current or there is no wire between P and Q. Then still there is a deflection in the magnetic needle. So without a conduction current, we have to explain the presence of magnetic field at P. So this inconsistency in Ampere's law. So according to Ampere's law, we are unable to find out what is the source of magnetic field at P. So there is some inconsistency in Ampere's law. So Maxwell has explained this inconsistency, explaining that there is a current even between the plates of a capacitor in the absence of a conduction wire. And this current he named it as the displacement current. Then the question comes, what is the source of this displacement current? So to understand the source of displacement current, he proved that the changing electric flux can also produce a current, and this current he named it as displacement current. So due to this displacement current, he has modified Ampere's law. Okay, look at the second point. Ampere's law fails to explain the presence of magnetic field at the point P. Okay, using integral B dot dl is equal to mu naught I, you can't explain why there is a magnetic field at the point P. But Maxwell modified this Ampere's law into Maxwell-Ampere's law, that is B dot dl integral over a closed loop is mu naught into I plus ID. So this ID is nothing but called as displacement current. So if you assume that there is a displacement current even between the plates of the capacitor, and because of this displacement current, you can explain the presence of magnetic field. Now let us see how do we explain the presence of magnetic field. That means how do we get the equation representing displacement current. So look at the first definition. Current induced due to change in electric flux is called displacement current. So we know magnetic flux is B dot A. Similarly, electric flux is equal to E dot A. Then differentiate this relation. d phi by dt is d by dt of E dot A. Electric field is changing with time, so bring area outside. A into dE by dt. And we know electric field between the plates of a capacitor, you can write it as sigma by epsilon naught or Q by A epsilon naught. A is constant, epsilon naught is constant. So when you cancel off this A and bring out epsilon naught outside, we get dQ by dt on the right hand side. This dQ by dt itself is called the displacement current. So we have got that. So we can prove that rate of change of electric flux d phi by dt is 1 by epsilon naught times of id, or id is equal to epsilon naught into d phi by dt, where phi is electric flux. So you can also write it as dE by dt in terms of dE by dt. See, from the first equation itself, if I write d phi by dt as id by epsilon naught, see this equation d phi by dt, if I write it as id by epsilon naught, you can also write displacement current in terms of change in electric field. So change in electric flux can produce displacement current, or change in electric field also can produce displacement current. So these are two equations, one in terms of change in flux, another in terms of change in electric field. Look at one more equation for displacement current. Okay, this is more simple. We know Q is equal to C into V. Okay, while charging of capacitor, so capacitance is constant, Q is proportional to V. So you can write Q is equal to C into V. Differentiate this relation. dQ by dt is rate of change of charge, which gives you displacement current, is C into dV divided by dt. So even this equation gives a formula for displacement current. So altogether you can express displacement current in terms of change in electric field, change in electric flux, or change in electrostatic potential. Okay, now look at Ampere Maxwell's law. As I told you, we can explain this concept or presence of magnetic field at P by making use of displacement current. So you can make this relation integral B dot dl as mu naught into I plus id. But remember, when I is present, id is absent. When id is present, I is not present. So if I apply this rule at Q, okay, if you apply Ampere's law at Q, we have only conduction current. If you apply Ampere's law at P, we have only displacement current. So between the plates of capacitor, conduction current is absent, displacement current is present. Outside the plates of capacitor, we have conduction current but not the displacement current. And in general, magnitude of displacement current is always equal to conduction current. Okay, now look at the four Maxwell's equation which led Maxwell to prove that light is an electromagnetic wave. And by using these relations, as I told you, he explains speed of light as 3 into 10 power 8 meter per second. And all the equations, or all these Maxwell's equations, you have studied in various chapters. So let us put them together. First one is Gauss law in electrostatics. It says integral E dot ds. Okay, we know integral E dot ds will give you electric flux is 1 by epsilon naught times the charge enclosed. Then Gauss law in magnetism. Integral B dot ds is 0. Okay, hope you remember its significance. Magnetic field lines always form closed loop. Monopoles do not exist. Then come to Ampere Maxwell's law. Integral B dot dl is mu naught into I plus id, where id is displacement current. Then Faraday's law of electromagnetic induction. Induced EMF is equal to change of magnetic flux, or integral E dot dl over a closed loop is d phi divided by dt. Okay, here last flux is magnetic, whereas in electrostatic flux will give you displacement current. Now come to properties of electromagnetic waves. Okay, so properties of light, in general we call it as properties of electromagnetic waves. See, when we studied the definition of waves, hope you remember we have defined it as a disturbance which transports energy and momentum. So even electromagnetic wave is a disturbance which transports energy and momentum, but it transports energy and momentum in terms of varying electric and magnetic fields. So if electric field oscillates with time, it generates an oscillating magnetic field and vice versa. So in the diagram, you can see electric field is oscillating along y-axis. The red line represents variation of electric field. It's a progressive wave. And perpendicular to that you have magnetic field along z-axis. So magnetic field is oscillating in z direction, electric field is varying along y direction. Then the direction of propagation is x. So the net wave or electromagnetic wave travels in a direction which is perpendicular to both electric as well as magnetic fields. So in general, direction is given by E cross B. The cross product of E and B decides the direction of light or electromagnetic wave. So if I represent electromagnetic wave by a travelling wave or a progressive wave equation, we know it's a transverse wave equation. Ey is equal to E naught sine kx minus omega t. Hope you remember, here x gives you the direction in which energy or wave is propagating, and the subscript to y tells you that electric field is oscillating along y-axis. Coming to magnetic field, Bz is equal to B naught sine kx minus omega t. So these two equations represent oscillating electric and magnetic field. X is the direction of propagation. Now look at some more properties. Just now I told you electromagnetic waves are transverse in nature. Okay, they can be polarized, whereas longitudinal waves do not show any polarization. They are non-mechanical waves. We know that mechanical waves require a material medium for propagation, but whereas electromagnetic wave can travel even in vacuum. It doesn't require any material medium for propagation. Coming to production, for producing an electromagnetic wave, we have to accelerate or decelerate the charge or oscillate the charge. An oscillating charge can produce an electromagnetic wave. Of course, even atomic transitions can produce an electromagnetic wave, but you can also produce it by accelerating charge. Then frequency of electromagnetic wave is equal to frequency of oscillating or accelerating charge. So if charge oscillates with a frequency 10 power 7 Hertz, the same will be the frequency of electromagnetic wave. Look at the next point. This everybody know, travel with a speed of 3 into 10 power 8 meter per second in vacuum. Okay, look at few more properties. What are the formulas that we use for determining the speed of a transverse wave? See, if you know the wave equation, speed is given by amplitude of electric field by amplitude of magnetic field, or omega divided by k. Okay, this we have already studied from progressive wave equations. The other formula which is important here is, you can also find the speed of an electromagnetic wave by using the relation 1 by under root mu epsilon. Okay, where mu is permeability of the medium and epsilon is permittivity of the medium. And if it is a free space, we know speed of light is represented by the symbol c. C is 1 by under root mu naught epsilon naught. So you know what is the speed in any other medium as well as speed in free space. When you divide these two relations, c by v can give you refractive index. See, I have written the last point, refractive index of the medium is c divided by v. Speed of light in free space divided by speed of light in medium. So that comes out to be under. Okay, now coming to the next point, energy density of an electromagnetic wave. Okay, we know energy density is energy stored per unit volume. And since electromagnetic wave contains electric and magnetic fields oscillating with time, the total energy density of electromagnetic waves is the sum of electrical energy density plus magnetic energy density. So I have written U dash as U dash E plus U dash B. And we already know for an electromagnetic wave, energy density due to electric field is half epsilon naught E square. But here you be careful, since electric field is not constant, it is varying continuously with time, we take its RMS value for calculating energy density. Hope you remember in the previous chapter I told you ERMS is E naught divided by root 2. So be very careful when you are solving the questions here. So half epsilon naught ERMS square plus half B RMS square divided by mu naught. So this formula gives me total energy density. Now this is a very small proof which is very often given as a 2-mark question. Okay, look at this proof. They may ask you to prove that electrical energy density is equal to magnetic energy density. Okay, for that start with electrical energy density. It's half epsilon naught E RMS square. And we know just now I told you speed of light is E naught by B naught. You can also write it as E RMS by B RMS. So if you make use of E RMS is equal to C times of B RMS, then replace electric field as C into B. It becomes half epsilon naught C square B RMS square. And again we have discussed C square is 1 by mu naught epsilon naught. Substitute the value. In 2 steps you can prove that UE dash is equal to half B square by mu naught. That means magnitude of electrical energy density is equal to magnitude of magnetic energy density. Since both have the same magnitude, when you add them, total energy density comes out to be epsilon naught E RMS square, which is also equal to B RMS square by mu naught. Again I repeat, here E and B are RMS values. If your answers are in peak value, replace it as E naught by 2. Okay, now coming to another term called as Poynting vector. It is a measure of energy flow per unit area unit time, and it's a vector quantity whose direction is same as direction of propagation. It is represented by the symbol S. S is equal to 1 by mu naught into E cross B. Okay, we have just now seen that electric field is oscillating along y-axis and magnetic field along z-axis. So if you know Ey and Bz values, take the cross product. J cross K will give you I cap, where I cap is nothing but the direction in which the wave is propagating. So from this relation you can write it as E naught B naught by 2 mu naught. I have written sine square kx minus omega t as 1 minus cos 2 omega t divided by 2. Again I repeat, sine square omega t is replaced as 1 minus cos 2 omega t by 2. Okay, now look at what is intensity of an electromagnetic wave. So intensity, it is defined as energy stored per unit area unit time. It is actually the average value of the Poynting vector. So if you take the average of S, just now I showed you that S is E naught B naught by 2 mu naught into 1 minus cos 2 omega t. Take the average of this. Average of 1 is 1 and average of cos 2 omega t, we know it is equal to 0. Since average of cos 2 omega t is 0, we will get I intensity as E naught B naught by 2 mu naught. You can also express it in RMS value as B RMS square by mu naught into C only in terms of magnetic field. Epsilon naught E RMS square into C, this is only in terms of electric field. So therefore you can write I as, okay, we know epsilon naught E RMS square is energy density. So I can be written as U dash into C. If you know the total energy density and multiplied with C, that will give you intensity of an electromagnetic wave. Come to pressure. Okay, we know electromagnetic wave can exert pressure and transfer momentum. So electromagnetic pressure P is equal to, it is same as energy density. Okay, hope you remember energy density and pressure will have same dimensions. So pressure is epsilon naught E RMS square, which is also equal to B RMS square divided by mu naught. So in terms of intensity, it is I divided by C. So but suppose the surface is perfectly reflecting. Like in case of a mirror, we know electromagnetic wave rebounces, making the same angle with the normal. So in such a case, it is 2I by C, but for normal incidence. If it is incident at some other angle, we have to consider the angle made with the normal. It would become 2I cos theta divided by C. Come to momentum of an electromagnetic wave. Momentum is energy divided by C for completely absorbing surface. And if the surface is completely reflecting, again the same. Momentum gets doubled. Transfer of momentum will be 2 mv, that is 2 times of E divided by C. But sometimes they give you a question where it is partially reflecting surface. If x% is reflected and y% is absorbing, then in such a case momentum transferred is x by 100 into 2E by C, whichever is completely reflected, plus y by 100 into E divided by C. Remember here E is energy of an electromagnetic wave. Now observe this table. Okay, this is what you need to remember, and you get a number of questions based on this table. Okay, the whole electromagnetic spectrum is classified depending on their wavelength ranges or based on the frequency ranges. If you arrange the various electromagnetic waves, so we know we have a number of electromagnetic waves, X-rays, gamma rays, UV rays, ultraviolet, infrared and so on. If you arrange them in a specific order, either increasing order of wavelength or increasing order of frequency, decreasing order of wavelength or decreasing order of frequency. So this orderly arrangement we call it as electromagnetic spectrum. So look at the wavelength ranges and the names of various waves as per your NCERT textbook. I have given the wavelength ranges, but exact division cannot be specified. Okay, so the exact division from radio to micro, it is not a perfect line of separation. So look at radio waves. I have given this in decreasing order of wavelength or increasing order of frequency. So for radio waves, wavelength range is anything greater than 0.1 meter. And you can look at production as well as detection. It can be produced by accelerating and deceleration of electrons in aerials. And coming to detection, receiver antennas or receiver aerials are receivers of electromagnetic radiations, radio waves. Next, come to microwaves. They have a wavelength range from 0.1 meter to 1 millimeter. They are produced by klystron wall or magnetron wall. You can find these walls in microwave ovens. And coming to detection, point contact diodes. Okay, you will study about diodes in the last chapter. So you can use a point contact diode for detecting a microwave. Then infrared have a wavelength ranging from 1 millimeter to 700 nanometer. Again, these are produced by atomic transitions or vibration of atoms and molecules. Okay, when you vibrate an atom, when atom gets vibrated, it releases energy in the form of electromagnetic waves, which corresponds to infrared. Then they are used in or detected by thermopiles. Thermopiles, bolometers are very sensitive devices which can detect the infrared rays. We can also make use of infrared photographic film for detecting these radiations. Coming to visible light, this everybody knows, 700 nanometer to 400 nanometer. And these are also produced when electrons in atoms emit light when they move from one energy level to another energy level, atomic transitions or electronic transitions in atoms. Next, it can be detected by your eye, photocell and a photographic film. Next comes ultraviolet, ranging from 400 nanometer to 1 nanometer. Inner shell electrons in atoms moving from one energy level to lower energy level. Okay, so these also is produced by electronic transitions and they can again be detected by using photocells and photographic films. X-rays, they have a wavelength range from 1 nanometer to 10 to the power minus 3 nanometer. X-ray tubes or Coolidge tube can produce X-rays. We'll study in detail about X-rays in the next chapter, that is atoms. Then coming to detection, photographic film, Geiger tube or ionization chamber. Similarly, gamma rays having a wavelength less than 10 per minus 3 nanometer, they have less wavelength but high frequency. Radioactive decay of nucleus. Okay, we know radioactive materials can emit alpha, beta and gamma rays. Alpha and beta are particle radiations, whereas gamma are electromagnetic waves. And they can also be detected by photographic film. Okay. Now coming to uses of different electromagnetic waves. Okay, generally they will mention the type of electromagnetic wave and ask you to explain any two uses of it. Or giving the use, you may get a question, identify the type of electromagnetic wave and hence find out its frequency or wavelength range. So if you remember this table, it will be quite helpful. So coming to the first one, that is radio waves. We generally use radio waves for communication. Microwaves, they are used in ovens and then in remote sensing. Infrared radiations, they are used for photography in fog and they are also used for physiotherapy. Visible radiations, we all know they excite our sense of vision. UV rays, sterilization. We know that water purifiers generally use UV sterilization. Then cleaning underground railway systems. X-rays are used for studying crystal diffraction and to detect fractures in bones. Gamma rays, They are used for radiotherapy and for detecting fractures in machines. So these are some of the uses of electromagnetic waves.